The 6th IAHS EGO International Symposium in Training for Resources Management. This is a keynote session. We concentrate on all the invited speakers to this conference in this session in order to give them the opportunity to speak in front of the plenary. So everybody is supposed to be here today. We have 6 invited speakers, and they will speak for 20 minutes each. They are expected actually to speak for 15 minutes, and then we will have, after each talk, 5 minutes of discussion. And I would like to invite all the speakers to try to stay in the 15 minutes time, and I will give a signal when 3 minutes are left. Now I'm pleased to introduce the first speaker of this plenary keynote session, and the first speaker is Professor Zaccarini. He has been Professor of Hydrology and Water Resources Management at the University of Bologna, and Zaccarini is now Professor of the Alma Mater. It's a distinguished club that puts together all the professors of the University of Bologna that recently retired. But I should say that Professor Bologna retired, but he's more active now than before. And he's been very active in platform casting. And I just would like to mention that he put into practice 10 real-time platform casting systems in Italy, Germany, and China. But his research activity spans over a wide range of topics. He's also currently member of the Commission on Environmental Risks of the Emilia-Romagna region, and also is currently the president of the Italian Hydrological Society, which actually he contributed to found. So, Ezio, the floor is yours. 15 minutes talk.
Okay, thank you for inviting me here. I would like to discuss a problem where I found many difficulties in the last decade. It's a problem of understanding and communication more than a real scientific problem. You know that decision makers have to take decisions without knowing what happens in the future. So we have problems at trying to understand what may happen. And this is what is called generally predictive uncertainty. Now, to do that, we use predictive models. But the models are wrong. They are not exact. And therefore, we need something better than that. What is important is to try to estimate the expected consequences of decisions and try to minimize the effects of wrong decisions. Now, just to show you why I'm very conscious about using models only, I have this very stupid example. It's just a reservoir, and my model is forecasting that the water level will not overtop the dam. And damages may occur when the dam is overtopped, and the damages have this nonlinear function. Where is the nonlinear function to express. Now, if I use my model forecast to estimate the expected damages, I will find them that they are 0 because they didn't overtop the dam. But being uncertain really of what will happen, this is not so. The expected value implies the probability density of what may happen integrated with the probability with a cost function. That is what we call expected value of damages. And it's obvious that this is not going to be 0. So predictive uncertainty is nothing else than an assessment of the probability of occurrence of any real future event, conditional upon all the knowledge we may have on the future. And that involves data, it involves one or more models. Now, I have a warning, and this is where we have been discussing for years. There is a total confusion about what is predictive uncertainty and what I define as validation uncertainty. And that has an origin on some notation used by the statisticians. Now, let me show you what is the difference between validation and predictive uncertainty. Validation uncertainty, I have plotted reality and model predictions, and we can do that. In hydrology, this is known as a scatter plot, but this scatter plot represents roughly the joint distribution of reality and model. And in general, what we do for improving our models, we know what has happened, and we look at the spread of our model forecast given the observation. Now, in this case, the observation has a probability 1 of occurrence because it has occurred. And the density is the density of the model given the observation. But this is not what we need, because damages are caused by the real event. So we need the probability density of the real event conditional on the model. And also because in the future, the only thing we know is the model, not what happens. So you see, it's the other way around. We have to cut the joint probability, knowing the model output, and estimating the spread of reality that has happened in the past, given the model forecast. And in this case, this is why I am laughing when people are always talking about structural uncertainty, model uncertainty, input uncertainty. In this case, what is real, what has probability of 1, is the model output. What is uncertain is what will happen. So please, in prediction, the model has to be taken as it is, because you have it. So what you have to do is to try desperately to estimate this joint probability. Now let me see and show you the benefit of using this approach. I have another example. I simplified the damage function. Now it's linear because I want to show you analytically what this involves. So we have a model that forecasts V hat. We need to decide how much we will release from the reservoir. And the damage function is, if we release water, we lose water. So there is a cost. But if we don't, we may have damages that will be a function of the value minus the max, okay? Minus what we release. The density, the predicted density in this case, is something that looks like that. It's the future value given the model forecast, but we can modify this density to include the decision variable. Because when we take the decision, we are releasing water, which means that it's like we are reducing the volume and we are shifting the mean of this distribution. Okay? So in this case, if we do the integration, we find out something interesting. If the forecast is perfect, the release is nothing else than reducing the level that we predicted down to the maximum of the dam. We minimize the water loss. But in the case where we are uncertain, you see, there is a small difference. It's the same quantity. This is our best estimate of the future value given the model, minus the max. And this would be in case this is perfect, plus something that is a function of the uncertainty, the sigma. The uncertainty expressed as a spread times a function of the cost. And this means that we have, if we don't know what will happen, we have to be cautious. and we have to release more than we would have done if we knew perfectly well. Now the point is, when we communicate this to the end user, we failed. We generally fail at making them happy with what we deliver, because predictive uncertainty has always been taken as a negative concept. What we have to say is predictive knowledge. This is our best knowledge we can predict. And I will show you why I'm saying this. You see, we can express our state like with this mathematical function. If we are totally uncertain, we can express this as a uniform distribution from -infinity to +infinity. If we are totally certain, we can express this as a direct function over the value we know. But in general, when we are uncertain, we have a probability density. But let me say that if we look at the glass in the other way around, we can call this no knowledge, we can call this perfect knowledge, and we can call this predictive knowledge. So if we have to communicate, in my opinion, we should communicate predictive knowledge. And this is the best we can do, and they have to rely on this predictive knowledge. What is the role of predictive models? The predicting models are tools aimed at increasing the decision-making predictive knowledge of future events. In other words, decision must come from a prediction in terms of probability estimate, which is integrated over the damages to compute expected damages. And they want to take the decision that will minimize the expected damages. So please do not consider models as the end of the process. Models are just simple tools which are wrong, but they are essential to build the predictive knowledge. I have two examples to show on the use of these predictive knowledge concepts. The first one is on the Lake Como, which is a beautiful lake in northern Italy, which had a tremendous number of flooding during the years. So how we did? Well, we built a simple predicting model, and the predictive model gave us a sort of density, which is the predictive density that I was talking about in the previous case. We integrate this density times the cost functions. Now, this function, this one represents if the lake is too low, you have ecological problems, fishery is ruined, and so on. If it is too high, you start having small floods in the main square of Como, and then you have all the shops wetted and flooded, and then you have to stop traffic in Como. So you have a sort of non-linear, highly non-linear function. So what we did, we integrate this function times the cost to get the expected value, but we also try to find out the decision variable, how much should we release, by expressing, as I said before, the predictive density as a function of the release. So you see now, if I release, I may lose water, but I will get an expected damage which is much smaller than the previous one. So we run the system with long-term optimization based on stochastic dynamic programming, based on transition matrices from 10 days to the next. But then, on a daily basis, we had a predictive model, and we could, during high flow season or low flow season, correct the long-term decision, the long-term rule to take into account these transients. And the results of this was exceptionally good, in the sense that this is the lowest level, this is the upper part, the level where they have to stop traffic, And you can see that there was an enormous reduction of these values. For the high values, it's not so easy because the volume of inflow is extremely large, but it can reduce enormously the frequency of the low values. And the benefit was some sort of 200 million cubic meters of water more, a reduced deficit, and 3% of increased electric production. So the whole system, and the lake user, I told him not to use the system until he was satisfied. After 6 months, he came back and said, you know, every time I took a different decision, it was the wrong one. So now he's using it since 1997. Every day he's using this. The use of predictive uncertainty in Aswan. Lake Nasser, this is not operational. The other one is operational, this is not. In this case, you can see something interesting. By operating with this technique and keeping the lake lower, you can reduce evaporation, which is enormous at the level of the lake. And we have done a simulation and we obtained that we can get an average of 2.7 billion cubic meters per year economized, where if you build the Jonglei Canal, you expect to get 3.5, 4.8 billion. But this is at no cost. It's just managing the lake, respecting all the constraints and all the uses of water, while this is at an enormous cost, environmental, social, and economic. So, conclusions. The use of predictive densities has been rarely used in practice because many reasons. One is there is a wrong assessment of the predictive density. Most of people use the ensembles. Ensembles are a representation of model boundary condition uncertainty. They are not predictive uncertainty. Others are just confusing validation uncertainty with predictive density. So this is one point. A correct approach implies the use of data, one or more models that have to be combined. Using the concept of predictive densities, you can use the probability density of the future value given not only one model, but n models. And this is essential to reduce the uncertainty. It is fundamental also to communicate properly what we are doing. We are not introducing uncertainty into the deterministic prediction. We are just communicating the correct form of our knowledge. And a corollary of this is that we have to demonstrate to the end user that this is working and it can improve their benefits and the robustness of their decision. Okay. Thank you for your attention.
We have time for questions, please, Luca. Thank you very much, Ezio, for this important talk. I would like to ask you a more general question. When you think back about your career in the past 40 plus years, in the 70s, early 80s, we had conferences about decision-making under uncertainty, hydrology, Hamburg, Oxford, you remember? So in this period of a couple of decades, what have you really learned? If you had to summarize it in one sentence comment, what is really the progress in decision-making under uncertainty in the past 40 years, from your perspective?
Well, I must say that from that period, I was in that period, and until I would say the 90s, I was totally confused on what to use. In the 90s, I got a contract from FAO. They wanted me to demonstrate the benefit of using a better flood forecasting system in the Nile, and what would be the return for using a better flood forecasting spent my time thinking, and I could not solve the problem until I found out that the only benefit was in the reduction of the uncertainty. And I could prove that using a more, a more dense prediction density, you could increase enormously the benefit, the robustness of the system, and the actual economical benefit. Since that time, then I could not solve the problem of predictive uncertainty. And I must admit, I was clarified with the concept by Christoph's work. I give him a tribute for having clarified to hydrologists the concept. And then I started studying the problem, and I went into the statistical literature, and definitely in the statistical literature there is a confusion again, not because for them it's very clear, but the translation of what they have done to other disciplines has increased the confusion. Because they predict quantities conditional upon parameters. And we forgot that these are not the parameters, in reality are our forecast. So elaborating that, I found that, and I think I clarified my mind on the whole process, from using models into prediction, into expressing the predictive knowledge, I would call it, and using it operationally in real time. So this gives you a reply.
We have time for one quick question. Or more. So, if there are no questions, I have one. And oops.
No, please go. I'll ask you later.
Okay, and I fully agree that the ensemble, distribution of the ensemble is not a predictive uncertainty. But actually, in validation, what we do is not to focus on an event. We focus on several different events, and so we look at the distribution that you mentioned in the vertical direction. So I agree that because in validation...
No, you're cutting in several places horizontally, because you know what has happened.
Yes, but we don't focus on a mixed value, so we don't look at the horizontal. But maybe that we can clarify it, because indeed it's. I agree that the validation uncertainty is not a predictive uncertainty, because there are also many other reasons like the operational uncertainty.
I have a small answer to that.
Yeah.
Okay. When you look at the expression of the validation uncertainty, you notice that in most cases the observation is out of the uncertainty band. And this is not possible in predictive uncertainty. In predictive uncertainty, the observation, because we are talking about the distribution of the observation will be 95 times within the 95%. And this is how you check that you have estimated correctly your predictive uncertainty.
Okay. Thank you, Ezio. And now we move on to the next speaker, and the next speaker is Professor. The next speaker is Professor Andreas Schumann. He is a full professor engineer at the Institute of Hydrology, Water Management and Environmental Engineering of the Ruhr University Bochum. Andreas Schumann is also a member of the North Rhine-Westphalian Academy of Sciences, Humanities and the Arts, class for engineering and economics. And he's an expert of flood statistics, design floods and flood risk management, river basin management, support systems, and water management systems. So we are really looking forward, Andreas, to your talk, and again, please feel free to stand up, or would you like to speak from here? Okay,
Thank you.
Good morning, everybody. It's a large topic for a short time span, and so I have to hurry up. I would like to start with some ideas about social hydrology. What is the meaning for me? And I continue this discussion we had yesterday in some way. Okay, we know that water management is the tool to adapt the hydrological conditions to the objectives and targets set by the social system. And so this was the development of water management activities, which can be shown, for example, if you have a look for the precipitation map in Germany, you see it's rather even distributed. You have regions with more than 1,000 millimeters precipitation per year, and other regions with 600 or 500. And this was set up of these large water transfer systems, which we built to set up car factories in dry regions or to devastate the landscape in upper dry regions using the same amount of water from these hilly regions here in the center of Europe of Germany. Okay, now then we started with IWRM. Our concern about water management activities were increasing. We introduced here the ideas that we should consider more the social welfare, that we should consider equity, the sustainability of these systems, and this was the starting point of IWRM maybe 20 years ago. But if you look for the hydrology, the hydrology is just a boundary condition of IWRM. If you look, for example, for these handbook of integrated water resources management set up by the Global Water Partnership, you will find that there's a need to assess the water resources, or the hydrological conditions are a part of the basin inventory. And I think this is not sufficient, and that's the reason why we now need social hydrology, because we have to accept that the hydrological conditions and the social systems have also a direct connections, not just over water management. There are also adaptation of the social system to hydrology and change of the hydrological system without any water management measures. And this is the point I want to stress now. With the example, let's say, for the flood management, you know, if we improve flood management, we intensify the damages because our technical facilities are limited. This was described in a perfect way by Di Sarah and others, and so I have not stressed this point more. That's his point. But an example from Germany, here you see the yearly flood peaks at the gauge of Dresden, and if you have a closer look, you see since the 50s large floods are became not evident anymore. This is caused by climate variability, but also by this large flood prevention system which was built up in the former Czechoslovakian Republic. But you see, if you have a look for the floods of 2002 or 2013, that the system is imperfect. It cannot manage all types of floods, and there are some failures because the capacities are limited, and you can estimate also the amount where we can manage the floods, or if you look, for example, for this quantile plot, you see that we cannot change or modify the large flood events, just a limited range of floods we can manage. And this is also the case with other water management activities. For example, if you look for the drought management, then we have the problem that if we increase, for example, the irrigation capacity, we will intensify the agriculture under favorable conditions. You have more water available, and then you will use this water in any case, and if the next drought will become more serious, you will have higher damages than before. And to give an example for this, let's have a look for the study we have done in the Chinese province of Shandong. It's situated here in the northeast of China, and maybe you know China produces more than 50% of all fresh vegetables in the world and 30% of all fruits, and many of them are produced here in this region, in this province, Shandong, and these fruits are exported to Japan, and here you see the steep rise of these exports of fruits. That means that agriculture is increasing significantly in the last 20 years in this region, but at the same time the precipitation became more and more low in this region. Here you see the differences in the yearly averages of precipitation. This is a process which is evident in the northern part of China. And of course, then the gap between the demand and the supply is increasing. How we could manage these things, it depends on your point of view. If you have an agricultural background, you think about irrigation changes, crop changes. If you have an engineering background, as myself, you are thinking about build dams and interbasin water transfers or other things. If you have an industrial background, you start to reduce the water demand of industries, for example, or to integrate desalination plants in the system. Or if you have a social science background, you are thinking about changes of legislation or changing water assets or something like this. Of course, you have to combine all these measures, but what's the most efficient way to combine them? And here we start with a very simple approach. It's an ABC model. Maybe all the people, as myself, remember this. It was set up in the 80s by Salas and Smith. It's a parsimonious water balance model. It consists of 3 parameters, A, B, and C. And you estimate the fluxes of water, just starting with the precipitation to the outflow of the system with these 3 parameters. Here it's the same model described in a little bit other way, but it's the same characteristics, the same equations, and the same parameters. If we set up such a model, for example, to describe the yearly water balance of our watershed, we could integrate now the demand of the industries, agriculture, or the domestic demand. And the normal way would be the reduction of the outflow of the system by the use of the water. But of course, this approach would not be sufficient because, for example, the agriculture depends strongly on the hydrological conditions. And you have here a feedback. If it's less precipitation, you will use more water from the groundwater. For irrigation, you will increase the evapotranspirations as a feedback, and you have to integrate it in this system. And to cope with these problems, you have to differentiate between green and blue water. I think you know this approach. We have here a combination of rain-fed agriculture, which depends on precipitation, and then we use additional water for irrigation, blue water, and so the basic component which we have to consider in such a coupled system is the soil water, because it's fed by the precipitation, and the deficit of water which we would have in the soil water will be used from the groundwater, and we enhance, of course, the percolation again in the groundwater, and so we have an internal cycle in the system. And we integrated this in our poor model, so we need not just 3 parameters, we need 5, C and D and E. For example, D is the parameter which describes the change in the utilization of groundwater, and B describes additional evapotranspiration caused by the irrigation in the system. And here we differentiate between the evapotranspiration from non-agricultural areas and from agricultural areas, set up these agricultural demand function, which is supplying the deficit to the precipitation, and we consider also the other human-induced water fluxes, which are shown here with these blue lines. Here we use statistical data for the use of industry or the domestic water supply. But the most important feedback mechanism is related to irrigation. We use the system for a watershed of 700 square kilometers, and it's fully operationalized. Here you can change here's the water demand, you can change the precipitation, and to make an assessment what happens in the system under these non-stationary conditions, we can have a look for the situation we had in the 70s, in the 90s, or today. And you see here 3 figures. This one is a groundwater balance change in the balance from year to year. For groundwater, here you see the agricultural water demand, and here you see the groundwater recharge, which is caused by the irrigation from agriculture. And here this would be the situation in the 70s, where we would have a surplus in the groundwater. This would be the situation in the 90s, where we have a deficit in the groundwater because we need much more water for irrigation. And here you see the additional percolation of this irrigated water. And this is the situation today with this average amount of precipitation. You see that the deficit of the groundwater is much higher because if we consider these relationships here. And if you compare it with all other measures I have shown before, for example, with the reduction of the industrial water demand, you see there is just one point where we could really be very effective in the change of the system. And if we make a cost efficiency analysis, and efficiency is defined in the change of the groundwater recharge here, then we will see that crop structure changes and irrigation technologies are the main points to modify the system and to adapt it to these changed hydrological situations. Now, the question is, are such changes feasible? There are many factors which determining the crop structure. Some of them are shown here. And our working hypothesis is that people are knowing what they do, and the actual crop structure is the result of optimized decisions of other individuals. And so the changes should not be so far away from the actual situations. We analyze the development of the different crop structures in the past from the statistics, and we have seen there are structures which are changing, which are varying, you could describe here, but other structures show a clear trend. And we describe these modifications in the crop structure with distribution functions. Here we use the Johnson distribution because we can there integrate the skewness, and the skewness is defined by the trend. So the upward trend, you use the upper skewness if there would be a downward trend. And then we make some important sampling. We modify the crop structures in the system accordingly to these distribution functions, which integrates the development and the trend. And we add an additional parameter, the acceptance. We say, okay, people will accept decisions which are very close to the actual situation, and they will reject decisions which are far distant from their actual behavior. And so we integrate these parameters as well. We made some stochastical Monte Carlo simulations, and here you see that our target area would be located here. We could improve the yield and reduce the water use in some way, and we have done this, all these modifications. We changed the crop structures, we changed the irrigation structure, and the output is shown here. You see here the actual situation, you see here options to change the water demand upwards or downwards, and you see there's a smaller part of decisions where we could increase the yield and reduce the water amount, and here we have the acceptance as an additional parameter. We have done this for the crop structure, for the irrigation techniques, and now we have some ideas what we could change without in a feasible manner. Of course, this is a very rough balance, and we improved it with a groundwater model. We used the FIFO model provided by the Basi company in Germany. And here you see, for example, the development of the saltwater intrusion. If we would not change the water demand of agriculture, you see that the saltwater front will move into the landscape, or far away from the coast. And now we started to make a reverse modeling. We estimated the amount we would need for an additional groundwater recharge to stop this saltwater intrusion. And we used then the information we had before. We started here with these parts of the watershed, and we set up the scenario of we need 202 million cubic meters of groundwater, additional groundwater recharge we would need, and then we distributed, we make here an assumption, and we have seen that we should go back to the 90s to provide at least, let's say, 8 million cubic meters. This would not be sufficient until we have to extend the changes, here the crop changes, also changes in the irrigation structure further upstream in this distributed mode. Okay, I hope you have seen that these feedbacks and interactions are very important to set up such measures, and so I come to the conclusions. Anthropogenic changes of the hydrological conditions are in many cases an interactive process. We change something and the social system change again and adapt again, and there are additional needs for changes. So we have an analysis of the adaptation strategies which is demanded for two-way coupling of hydrological conditions and human-induced impacts. We have seen this with a small example of irrigation. And most important, the acceptance of limits to adapt the hydrological conditions to social developments is in a sustainable way is very important, and this means for me social hydrology. Thank you very much for your attention.
We have time for questions. Okay, please.
Yes, I have one. In your modified ABC model, you currently model all this stuff with a set of linear equations. Don't you think nonlinearities and pressure effects may also play a role in this?
It's of course it's related. We use it for yearly water balance. Yes. And these characteristics we derive here were estimated from a more sophisticated water balance model, which we applied with statistical data. And we have seen that, okay, nonlinearity could play a role or plays a role, but we could not specify it completely. Yes, we had just these long-term averages. Yes, but we integrate nonlinearity in the agricultural water demand, as we have these cycles of the recharge.
Other questions? Please, Stephen.
Question. So, it seems similar to the earlier question. The model that you presented, the modified ABC model, came across to me as still a hydrological model. Are there feedback that you're talking about from the hydrological human? Are you actually modeling, for example, human population dynamics or demographics and stuff like that?
Okay, I did not mention that. We use the agricultural water demand of today. You could also change the agricultural water demand, and it's included here as a form of the potential evapotranspiration. Of course, if you change the crop structure, the evapotranspiration will be changed, and we use it for today's crop structure. Yes.
Okay, very quickly.
Yeah, I think on top of that question, it also looks to me a little bit like a one-way road. It looks like we hydrologists are informing the other sphere, the social decision-making, and they have to accept the limits that we, as experts, impose and say this is what they can take, but we are not so much informed. The hydrological decision-making is not really informed by social considerations, interests, politics, and so on.
Okay, we considered at least development of the agricultural structure in the region, knowing all the crop changes. We considered also that the people are now able to decide by themselves what they grow there. We considered that the people are using the groundwater directly, just paying for the electricity. Yes. Of course, you could set a much more complex social system model, but I think we consider the social system as the boundary conditions of hydrology.
And so he said, okay, it will not be changed in the next 10 or 20 years. Maybe it will be changed. Maybe there will be correlations between the farmers, or there will be a change of the legislation. But he has just to look for the hydrological social conditions as they are now, and he extrapolated them.
Thank you, Andreas. Very nice talk. We now move forward to the next speaker, and the next speaker is Peter van der Zaaij. He is professor of Integrated Water Resources Management at the UNESCO IAHS in Delft, and Peter also holds a professorship at Delft University of Technology. At IAHS, he chairs the Water Management Group, and he also head of the Department of Integrated Water Resources System and Governance. What is noteworthy of Peter is his long-term work in developing countries from 1982 to 2003, and he's also an expert in curriculum development for water resources management in developing regions. Peter, just 1 second, I start the presentation, and here it is, and the floor is yours.
Okay, thank you very much. Thank you for your kind words. What I want to do is to contextualize in my presentation social hydrology from my perspective. A very limited perspective, it's a bit an ambitious task. I hope that I succeed, but you can decide later. The title is rather ambitious, I would say. We all want to understand society-nature interaction, whether we are social scientists, natural scientists, engineers. I think there is a common objective that we have. What is urgently needed is to have, let's say, bridging concepts where we can productively engage between engineers, social science, and social science. And that is apparently problematic because there's no consensus. We normally, scientists normally privilege certain types of methods and theories in response to how they were trained. And that's what we see everywhere. So everybody has a partial perspective to the same thing. Different epistemic communities of scientists may study the same object and yet see different things. And see things differently as well. And a nice example is, I think, the terminology on one hand, social hydrology, and on the other hand, hydrosociology. Now, when Siva and al. Wrote their paper on social hydrology, they didn't even cite some of the people who in the 1990s used the concept of hydrosociology. It shows that we are not communicating. And there's hardly any cross-disciplinary learning, and this is obviously suboptimal, because we are sitting in our local optimal problems, but there may be a global optimal that we don't know. And in this paper I try to inventorize some of the disciplines that have been interested in understanding society-nature interactions. And there's different terminology. Some call them CANs, C-H-A-Ns, others SES, others SES, and now I decided to call them SHITs. Social, hydro, ecological, technical systems. And I think it's important for me, because that's where the engineering comes in. Oops. So this is actually a very gross simplification of the field, of the core disciplinary field, that I think that made an interesting contribution to analyzing social water interactions. Political geographers, institutional economists, system ecologists, I call them briefly, and hydrologists. And I want to briefly review them very, very quickly. So, of course, if we start with the institutional economist, we think of the framework developed by Eleanor Ostrom, depicted here, but also further refined, I can say, by Claudia Paul-Bossel in this very nice overview. But you also have in this field, for instance, scholars who work with agent-based models and game theory. This is a nice example of Marco Jansen on in agent-based modeling. So they are concerned with rules, incentives, and sanctions. And that is basically, you have to summarize it. That's what they are doing. Now we move to political geography. That's a completely different ballgame. First of all, they don't use nice graphs. So as I can see, as I will show in the others, they have formulated, they have beautiful formulation. And this is a quote from Erik Zwijndal, who is a Belgian guy in Oxford, I think, who already in the 90s talks about social nature. And talking about nature and society being hybrid. Nature and society are deeply intertwined. You cannot operate natural ecological conditions do not operate outside the social yard. More recently, Erik Zwijndal and Karen Bakker introduced the concept of waterscape, and I just want to mention this because this is a terminology that may resonate with hydrologists who use landscapes. For instance, Jessica Butts from East Anglia writes, waterscapes comprise assemblages of a wide range of water flows, technologies, issues, institutions, discourses and meanings, and which produce and are produced by power relations. Now, these political geographers always use the P word, power. Everything is power. That water doesn't flow to downhill, but it flows to where the money. That's what they tend to say. And they are very much concerned with, let's say, equality, inequality. Let's move on. Now we go to the system ecologists. It has been mentioned already by a few presenters. Talk about complex systems, resilience, robustness, self-organization, blah, blah. They make very nice graphs. Like these S's and fold bifurcations. Really beautiful images they use to understand, first of all, natural processes, and then they have the audacity to extend it to society. And Martin Scheffer, for instance, studying lakes, distributing the lakes, etc., beautified lakes, and then he said, I can also model this in society. Similar process. So there's a typical arrogance of the natural scientists, which we also see amongst ourselves, which is not bad. It's another image of how social sciences and ecological sciences incest modeling together in this field, and then of course other nice graphs like this. And a lot of people think that this is real. But of course this is just a model, and the model is wrong. But we should never forget that these are just devices to obey a certain simplification of reality. Finally, we go to the hydrologist. I first mentioned eco-hydrology because I've learned that the eco-hydrologists at least have contributed this idea of optimality and co-evolution. And I think that's a very interesting approach. I have a quote here of Bettina Schäfli. The complex interplay between biotic and abiotic processes shapes the constantly evolving landscape. Whatever properties it has today are the legacy effects of the history of its evolution. Now this formulation can be understood by Jessica Butts, I think, as a political geographer, and vice versa. So there is, I think, a linchpin. There's a historical perspective. There's not the power, the people. And then from here, it is not a big step, I think, to social hydrology and introduce the Shiba et al. Also using this word of co-evolution. And I think that is useful. What I here indicate as important for the eco-hydrology is the G, gravity. And the political science always say it's politics. Of course, everything is politics, but also everything on Earth is gravity. And it is both. And that's the obvious thing. And, okay, so this is my image now of the field, the simplified field that I think we should contextualize social hydrology. Eleanor Orston et al. Say it's incentive stupid. Perhaps you hear more about it. And then the political geographer, everything is political. The system of ecologists talk about tipping points, etc. And then yes, we can model everything. And I'm not trying to ridicule it. I think that's it's a marvelous energy to go forward. But we should take cognizance of the field and benefit from the insights that we have. One big thing is, what is there in the middle? And that's my big question. I think in the middle is Norgaard's work, in co-evolution. I think that is where things are neatly tying in. I want to make 5 points on this. This concept of co-evolution is used by Norgaard. First of all, does justice to the historical dimension. Social scientists always look at history. Natural scientists, like Bettina said, also looks at the landscape in a historical perspective. So that's important. It also does not privilege one type of science over another. And I think that's another very important issue. Third one, it can deal with inequalities in power. I have a few very nice quotes of Norgaard on this. And so we have to take account of power in this integrated models. Fourth, it creates space for learning and science. Norgaard has been working his whole career in the California Bay and actually shows that science is endogenous to the system, to the complex system that we model. And he's part of it, and we are part of it. And that is, I think, very important. And the second related point is that, in that sense, we also realize that science is context dependent. It is not neutral. We can only find the thing that we are looking for. So we have to be aware of it. And this resonates well with scholars of the social studies of science, social technology studies. Finally, it can deal with a big debate in social science between the actor-structure dilemma. And again, a nice quote. So co-evolution is a field that we could study more in detail and see how we can benefit and link with other fields. Now I want to go back to the social hydrological models that have recently been produced. I think there's a flurry of models coming out, especially by students of Siba and Gunther and Huub, which is very interesting, I would say. And Juliana, of course. Just quick, a few images. So this is Louis' model of the Danube Basin in China. This is of all these four models that I cited, the most straightforward. And it basically traces 4 state variables, if I'm not mistaken: vegetation cover, water storage, irrigated population. Now, this is Van Emmerich's model. So he has, Liu had 4, now Van Emmerich has 5. It is population, irrigated area, capita, hydrology, ecology, and environmental awareness. Now it becomes more complicated, and it is El Shafai. He has 2 loops, and he has in total, I think, 6 or 7 variables, like community sensitivity. Okay. And then there's the model by Giuliano and his co-authors in 2 papers, who have 7, I think, state variables. And then some nice equations. So my question is, do these models include the right parameters and processes for the right reasons? Of course, I don't know. But I think we should think about this. First of all, I checked in this nice paper, which Tina also mentioned yesterday by Sina on these syndromes, and she identified a number of factors that are underlying these syndromes that she identified in a meta-analysis. So, population, water demand, infrastructure, exogenous shocks, ecological consciousness is taken care of in most of these models. However, effective reallocation of water across sectors, effective control over water, basically meaning effective institutions, and resource capture by elites, let's say power, not accounted for, as far as I can see. So, how are we going to deal with this? I think that's a practical question. Second point is that I think that some of the parameters used are too much lumped and blunt. Like environmental awareness, as modeled by Van Emmerik, I think it's too simplistic. And it is like an exogenous factor, only influenced by the state of the environment. As if farmers in Holland, okay, this is about Australia, I don't know the Australian farmers, I know Dutch farmers, they are not going to reduce their income because they have now become environmentally aware. They're not going to do that. But that farmer, I haven't seen. So we have to find another way of making it more analytically sharp why certain things happen. The second point is that some of the parameters should be inside the model, should be dependent variables rather than independent variables. And the example I would take is in the model of Giuliano, flood risk awareness. I don't know if you agree. Okay, I have no time, so I just want to give one example from outside our world, on asymmetric common pool resources, which we find in water. The upstream, downstream dilemma. We have a river, we have a canal, some irrigators, and it's extended, and then you have the classical head-tail problem. The guys near the water source have easier access to water than downstream. So what happens? Janssen has done very nice agent-based modeling in an experimental setup and finds this. Head-enders, in this situation, appropriate more water than the tail-enders. However, they don't take too much. Because, okay, they don't, and the second point is the tail-enders, they get somewhat, but they invest more in terms of maintenance than their head-enders. Now, then you would expect that such a system would collapse. It doesn't. Then he says, we have to add communication. And Lade says, we have to add a factor social ostracism. Now, that's an interesting one. How do you measure that one? My student, Kondakej Hans, has studied this, but not in an experimental setup, in the real world, in Tanzania. And he finds head-enders indeed appropriate more water. But they also invest more in coordination, which resonates with a nice paper by Bologna IAHS. The status quo has been maintained for more than 100 years, so this must be a sustainable system. That's why we studied it. These are all indigenous irrigation schemes. What we find is that heterogeneity is the key word. The differences make the thing tick and knit people together. In soils, crops, spot ownership, kinship, they create mutual dependencies and multiple loyalties, explaining system endurance. And the beauty is that these type of things can be made explicit and can be sketched or traced or even inscribed in the landscape. And that's what we are good at as hydrologists. Just an image in Tanzania. You see, an irrigation engineer would never design such an irrigation canal because probably he was drunk or so. But this is the real thing. In co-evolution, this is a 100-year-old canal, and the tree has grown around. This is a nice example of co-evolution. Okay, and what he finds is that there's inequality. 50% of the farmers own 50% of the water and the land, and still it works because of kinship, relationship, and people have plots in different irrigation canals. Okay, last slide. I think co-evolution is a good candidate to tie up various disciplines. It will always be interdisciplinary endeavor. It must include tangible indicators, also the social dimension. And let's not lump funny fuzzy concepts too much, because that will not help us much, especially if we want to change things in the future. We have to find the right balance between process-based bottom-up approaches to learn top-down processes. We have to identify some key bridging concepts, such as the landscape, but also epistemological principles, like the principle of symmetry, no time to explain. Lay and academic knowledge and technology should be included in our models, because we are part of it. And that has a practical implication. We have to construct facilities of learning in real-world sheds. And they are already existing. For instance, California Bay, Naivasha, Kenya, Nkomati, we are working on it in Southern Africa, the Blue Nile, Mekong, Murray-Darling, and also, I think, urgently in endorheic systems, like under stress, like Chad, Iraq, RLC, Turkana, Dead Sea, Okavango, etc., etc. Pitfalls, we should acknowledge the danger of water determinism. Water is not the driving factor of. We have to be careful there. For instance, it could be energy, it could be other things, which then should be included in our models. From simulating past patterns to predicting future trends is a big step, and that requires models that correctly simulate the processes for the right reasons. And from here, it is a small step toward a normative and progressive project that we, with such integrated hydrological models, could be striving for optimality in the normative sense, meaning that our water systems will be serving our people better, more inclusively, and also for ecological sustainability. Thank you very much.
Thank you, Peter. We have time for one question. Please, you.
Yeah. Peter, this was a great presentation, and I like the way that you use existing old systems to analyze what went right, but are there not many collapsed systems from which you can learn what can go wrong?
Well, yeah, yes, I think that has also been tried in the past, but also for, I think in Arizona there's some beautiful studies. There's some beautiful studies of ancient societies that have collapsed. Perhaps due to climate or perhaps due to other things. I agree.
Or even the successful systems may have had periods during their lifetime where things were wrong, after which they changed the system.
Yeah, that's what we are trying to model, I think. We're trying to make do with a system that is for 90% human-made, and it is evolving all the time. And the science is also evolving in this process.
Sorry, we have to move forward to the next speaker. Thank you, Peter, and congratulations. I'm now pleased to introduce Berta Reimer, the head of the hydrological research at the Swedish Meteorological and Geological Institute, and she's also professor in water and environmental studies at Linköping University. Berta has a wide range of interests in research, hydrological forecasting, integrated catchment modeling, water quality, and also I would like to mention that Berta is leading a European project, Switson, which aims to create a database of open data and information sharing in hydrology. So, Barry, the floor is yours.
Okay, I will try to limit myself today to speak about hydropower, and I will speak about river flow in Sweden, so quite some limitations. I've just shown you where Sweden is in the northern part of Europe, and it's 450,000 square kilometers, and it's the responsibility of my institute to provide society with water information for all this surface area. So this is what I'm going to talk about. And hopefully can give an example of interactions between society and hydrology. Okay, Swedish hydropower of today. We have 200 larger hydropower plants. We think they are larger, but in the global context, I guess they are quite small. And actually, they produce about half of our electricity consumption in the country. But then we have also almost 2,000 small hydropower plants. And they have rather limited production capacity, but they have large impact on the ecology. And if you look at the pros and cons for hydropower, this is why I had this provocative title of "You Speak Electricity versus Ecosystems," because this is an upraising debate today. When you have the climate change and you have the pollution and so on, then hydropower is considered as a very clean electricity. You have no waste, you have no greenhouse gases, it's renewable, and in Sweden we have a large potential because we do have a lot of water and a lot of lakes, and we have mountains and so on. So it's good for hydropower. Consequences are that we have huge biodiversity losses, ecological barriers, they kill fish, you fragment the river, we have dry river reaches, it's no beautiful landscape any longer, it has consequences on tourism and on people's recreation possibilities. You change the transport of substances, we have erosion problems, and well, we can also have problems sometimes with the high flows, because if you have a highly regulated system and we have long rainfalls in Sweden, then you need to speed water from the dams eventually so that they will not break down, and this will also create problems sometimes if this is not done in a clever way. And there is also claims that they increase the mosquito production. And this is, of course, a severe problem in Sweden. In some areas, actually, cattle die because the mosquitoes are so intense. So, as Pantarei should also have some long-term perspective on things, I would like to go back 100 years and look at the development of hydropower in Sweden and how this has affected research and decision support. Here we can see the interaction actually over time. Because these ecosystem problems is not new, and it's not the only problem that we have had with hydropower throughout the years. So if we just quickly go through this, when we started producing hydropower because we needed electricity for the industrialization. So, and then we put a lot of efforts on mapping the hydropower potential, and actually this is when we mapped the whole country, all the water divides, river reaches, falls, and so on. Then those hydropowers come in operation, and very early they needed spring flood forecasts. This was, of course, an issue already at this time, so I was, of course, not there, but my institute started to produce such forecasts already at this time, with the means that they had. Then you had the first actual problem, that is that they reduced the ice stability. And ices were very important in Sweden at this time because we didn't have a road system. So most of the transport was on rivers, on heavy transport on the ice during winter. So we actually had a huge department then only working on ice stability. And then during the 50s came this with the environmental concerns. And then we had the oil crisis, and actually then we needed more efficient production, and this is why we started with the HPV model. It was the hydropower industry that actually made the development of developing this numerical tool in Sweden. And we realized that we could use this tool also for flood forecasts for civil society. So we started our national warning service for floods. And then also we started this that I mentioned before to coordinate the speeding rivers at high flow situations. So we have working groups for that. And well, in '85 we had a major dam break. So this of course started a discussion about safety and design floods. And we started to work on that, and then came the issue of climate change, and we had to redo all those calculations, taking into consideration a changing climate and other precipitation snow volumes. And now, eventually, during this decade, the Water Framework Directive was introduced in Sweden, and they talk about ecological status. And then diffuse pollution and hydromorphology. Hydromorphology, yes, are two of the major stresses for ecological status, and this also is caused by hydropower. Now, I would like now to insert some pictures, because we have just digitized our archive, and we have a lot of nice pictures, and I think it also gives a dimension of how people actually performed their work 100 years ago. This was the situation. It says a lot. Those guys, they were out mapping the water divides, and here you can see one guy monitoring the fall and with a gun beside him. So I don't know why. And here you can see the equipment they used and the lack of equipment. And you can see one man here is fishing at the same time as he is actually conducting his measurements. So it also tells you a bit about the work that they performed. And here you have one major idea of how the landscape changed. You have the Porteous Dam in 1910 and then in 2010. So it's quite a big shift in landscape. And of course, a big shift in water flow. Here are two examples. The lower one is at the outlet of Lake Vänern, and you can see that there we have actually increased the high flows, because this is a huge lake, it's the largest lake in the European Union, and we take a lot of water out of it to create energy. And this river discharging to the western part of Sweden is very sensitive. It has some glacial clays that are very sensitive to landslides. So here we have a lot of problems on concerns on that part. And on the upper panel you can see one typical river from the north, and you can then see that the high peaks have actually diminished, and now we don't get those high flows any longer, but we have this very intense short-term regulation, of course. So this is the shift you see when you regulate the flow. This is examples, historical examples again, about the ice surface. So we had like 50 persons working with this, but then they diminished when the road and the railway system came along. This is also interesting. This is from the numerical modeling. This is in 1970s. This was the technical environment when we did our numerical forecasts. And this again is this Novikovsky dam that broke in 95. It was a major break. We actually do have regular breaks, but normally these are the small dams that break, and it's not so serious. But this was, I don't know, some million cubic meters that flushed down the river. So no one was killed though, which is quite surprising, but this is up in the mountains and in the forest, as you see, so not many people live there. But this is the workflow also, how we do our calculation for flood, design floods. This is an example of the workflow when it comes to climate change, going through all those different climate models, downscaling procedures, bias corrections, end user discussions, dialogues, and taking new information, introducing to different end users. Okay, back to ecology. This is the latest report from the European Environmental Agency, showing on the left the ecological status in the water bodies for each country and the member countries of the European Union. And you can see the red is bad, green is good, and the blue is perfect. So then you can see how your country behave. And for Sweden, we actually have rather good conditions. But if you look at the impact side, the stresses, you can see that this is, I think it's orange on this, red on this panel. Then you can see the hydromorphological stress that we have on our water bodies. So these are quite large for many countries. So it's actually one of the major themes that they discuss now. How can they improve this for Europe? So I'm coming back to this with open data, what we have done at SMHI is that we have opened our archives, but we have also a website only with water information that is open and available for everyone, and also for water authorities. And we actually developed this page together with them, and also they decide what kind of information they want as decision support. So they get time series of observed data, they get model data, and we work on a very fine scale, actually 37,000 subbasins. We deliver information for all those modeled information. And this was actually what I was going to speak about today. That for those, all those subbasins, they also want information about the degree of regulation. They want locally regulated volumes, total degree of regulation, on all upstream catchment, differences between regulated and naturalized daily water flow. And you can see the different variables. And now the next step is that they also want short-term regulations. So I don't really know how we will manage with this. So this is actually the main results from my paper in this red book. So what we have done, based on all those 37,000 basins, we have also aggregated results for the complete country, for the entire country, to see how the river flow, surface flow from land to the sea actually has changed over time. And you can see here that we have actually shifted, that's the point with the regulation in Sweden, to shift water from the spring peak to the winter, when it's cold and dark and we need electricity. So this is the shift that you see, and this is what we want to do with hydropower. But actually the peaks have, the flow peaks have been reduced by 15%, and altogether it's about 20% volume that is shifted between seasons due to regulation. So then I have, and this is also in the book, you can read more carefully about how we did this, the predictions. We use a model, it's a process-based numerical model. It's called HYPE, and it's set up all over Sweden, all over those sub-basins, and it's an open source code, and you can download it and play with it if you want to. And then we have the monitoring system where we can evaluate the model, and we actually release this model system in new versions at least every second year to improve it and update it and refine it. I see, Alberto is So I will not go into details, but just to show you a little bit of how we are doing and the detailness we have. Like we have a lake routine, and we model explicitly over 9,000 lakes, and we use a lake routing curve, a rating curve, and this is calibrated individual for lakes where we have observations. And then we also calibrated group-wise, downstream monitoring stations or for regions. But then we also have a general rating curve for the rest of the lakes. And then we have like a regulation routine, and it's very simple. At low water level, production is reduced. At moderate water level, the outflow depends on the season. You saw the seasonality before. And when the dam is nearly full, it uses the spillways. And the spillways flow is also calibrated and using this rating curve. So then we estimated the present flow, that's the regulated flow, that's what you can actually validate against observations, because this is what we have to do. And today, and in the model, we then have more than 500 regulated lakes with individual storage volumes. We have 23 man-made river diversions, and then we calibrate the spill and fill after seasons, after observations. The naturalized flow, we have then reduced this regulation storage, and all the man-made lakes, they were only 3. It's normally original lakes in Sweden that you regulate. For 30 major reservoirs, we have an individual lake rating curve. It could be based for historical observations, or it can based on the spin equation that we have. So, you can read more about this, but this is something about the model performance in general. We evaluated it, I think this is based on 10 years and for 400 stations. And you can see the model performance in blue for non-regulated rivers, and in red, there we have the regulated rivers and of different sizes. And for 8 dams, we did a specific evaluation of the model performance, because there we had independent estimates based on observations that were independent from our model, so we could actually check the model performance. And these are some curves on performance for specific dams. I will hurry on a little bit because this is very detailed, so you can read about it. It's better. And I mentioned before that the redistribution between seasons is about 20%, and the peaks have diminished by 15%. I think this is important because when we estimate effects of climate change, for instance, we think that the peaks will be reduced by maybe 10% in 100 years perspective. So this is actually a more, well, has more impact on water flow and high peaks in Sweden than the climate change. Yes, I will not go through more of this. I will end up by just, well, hoping that we can have both electricity and ecosystems in the future, and I show you again the production of electricity in Sweden. As you see, we don't have much of fossil fuels production, but we have nuclear power. So of course, if you don't want nuclear power, you need to replace it. But it's also interesting with this figure. The green one is the total consumption, and you can see that after, well, from the 80s, we have not increased the electricity consumption in Sweden. And I think this is a bit surprising. But it's also that we have moved the industrial production to China, haven't we? Because we import all the stuff from them. So this is what happens with globalization. And finally, I want to come back to this one, speaking about Cartago and Siva yesterday. I think when you look now into the future of water research and how we can support society, I think we should reflect a little bit about the role of the scientists. Because we can act in different ways. This is an example from Hilke, where he describes how we can act as pure scientists, just producing raw figures and publishing papers without concern about societal needs. We can be this kind of advocate who actually wants to achieve something, who wants a specific development, and argue in a specific way. We can be this science arbiter, I don't know how you pronounce it really, but that's when we actually ask questions that society put to us. We ask them about, we try to answer and solve problems that we see in society. And then we can also be this honest broker, which is more that you provide different options and having a dialogue with the end users to see and make them actually understand in their decision making how they can use our results. And this is much more, I hope you understand, this is much more than just getting the data out in the paper. So here I think we should have a discussion, at least so that we are aware of which roles we play when. I think this is important. So this was my final contribution to Pantarei. Thank you.
Time for one question. No questions?
Okay. Oh, sorry. Just a curiosity, Barry. Thanks for the very nice presentation. You showed us that you can model quantitatively the impacts on the stream flow regime for the whole country with your numerical model. Did you try already to assess quantitatively the impact of the environment in terms, for example, of habitat suitability indices as well, or?
No, actually, we deliver only those variables. It's like 10 variables with different indices on the hydrology and how it has changed due to hydropower. And then it's the water authorities who translate this into some kind of ecological status. That's not our responsibility. So we just, we talk to them and deliver it, and then it's they.
Pure scientists, then.
Thank you, Barry. Thank you, Barry. Again, and I'm pleased now to introduce Professor Tommy Evans from the Department of Geography at the Indiana University. He's also the director there of the Center for the Study of Institution, Population and Environmental Change. He's an expert of human-environment interaction, human dimension of global change, land use and cover analysis and modeling and decision-making. He was also co-awarded the Sustainability Science Award of the Ecological Society of America in 2009. So, Tom, the floor is yours.
Thank you very much, and I hope I don't pollute your nice conference with a little more social science. But what I'm going to talk about today is kind of the intersection between governance and learning and water management. And I'm going to take some motivation from this slide here, which is from the United Nations Environmental Program report called a Global Environmental Outlook. And what it shows is what we've been talking about here quite a bit, is the uncertainty with our models. Of course, as you go farther out in time, you get more uncertainty, but the key thing I want to focus on here is the agriculture bar, and that shows that there's this big, huge uncertainty with regards to what the possible water withdrawals will be in the future. And a possible intersection or crossing of the industrial uses versus the agricultural uses. And much of that is dependent on how irrigation will be used and the efficiency of irrigation water globally. And this slide, we can argue about the methodology behind the production of this slide, but what it shows is that there's varying degrees of efficiency in irrigation depending on how people are moving water, what the infrastructure is for water, and what crops are being grown. But you can see dramatic diversity, particularly in Australia and Asia. South Asia, there's a very low efficiency. In Europe and United States, some moderate efficiency. And then coupled with this are what we heard a little bit about just now is the development of medium and large scale dams globally, and so we see some hot spots of dam development. But basically there's an intersection, and governance is effectively at the link between these kinds of irrigation systems, these dam systems, and so on. So what is governance, and how can we unpack it a little bit? Well, this is going back to that same GEO report, GEO5. This is produced every few years. And there's a kind of a scorecard that is produced for each of the chapters. Water is one of the chapters, and there's other chapters on air and land and so on. But this is just a few of the scorecards, and I put a red bar around the letter grades, and I think we're all familiar with these from A to F. And what it shows is that there's a kind of failing score, near failing score in a couple dimensions. I know you can't read all these words, so let me unpack it a little bit. One is related to the goal of developing adequate monitoring systems. And so this is one core point I want to make today. I've got two core points. The first is about the tight coupling between governance and monitoring. And so the goal is a comprehensive, or the gap is the comprehensive monitoring systems will continue to be limited by funding and capacity. This is the gap. And what they say is needed is metadata on existing data, agreed quantitative targets on comprehensive monitoring and reporting systems. So this is what this report is saying as the challenge here for monitoring. And then the other key one I want to focus on is related to the development of integrated management strategies. And what the gap that is articulated in the report here says is that developing countries in particular will face difficulties implementing integrated management approaches, lack of funding, capacity, and governance. So they say that there's relatively good progress in developed countries towards developing integrated management strategies, but that the developing countries are falling behind. And what's needed is reporting mechanisms and meaningful governance indicators. And so I put it in red intentionally, governance indicators, including the effectiveness of such approaches. So how do we do this? So looking at, I quickly looked at the vision paper in the blog that was up on the website last night because I was still jet lagged and I wasn't sleeping. And what it references is kind of this history, this legacy of trying to pack the social and hydrological together. And I want to make one kind of point that these optimization models, there's certainly a place for them, there's certainly utility in those. By all means, they're great for getting stakeholders to think about outcomes that wouldn't otherwise have been considered. We know there's this kind of difficulty with the predictability of these models. So what can we do to try to tighten that bar that was discussed earlier, and how can we also design systems for adaptive governance to enhance robustness, and how can we incorporate this kind of adaptive governance into our models? So as opposed to having governance as an outside exogenous component to our models, how can we make it endogenous so we can understand how a system is responding to different kinds of social and ecological systems? And here I want to reference some work that was quickly mentioned before, and that is some work from Lynn Ostrom about the design principles for successful common pool resource systems. And I won't go into this into too much detail, but there's these kind of aggregation of case studies that have been shown to identify situations that tend to lead to effective governance. Not always, but tend to. And those kinds of dimensions are these as follows. Clear resource boundaries, that is being able to identify the resources being extracted. Collective choice, the ability of users to have some kind of voice in the management of that resource system. Graduated sanctions, that is a very minor sanction the first time you do something wrong, a more serious sanction the second time you do something wrong. Mechanisms for conflict resolution, that is this upstream, downstream communication that we heard about before. Recognition from higher level authorities, that is a formal, legal, institutional recognition of local level management. And then going down to these important ones here, rules that are adapted to local conditions and effective monitoring. Now, what does this mean? And let me try to unpack this a little bit in terms of what is meant by governance. And the work of water governance and common pool resource systems governance uses this term institutions. And let me use a definition and a story to describe what that means. Institutions includes the formal and the informal rules, the social norms, and also the legal institutional framework. And at the risk of going over time, I'm going to tell a short little story. I was in Nairobi doing field work last week, and this is going to sound a little bit like a joke, but an American, a Kenyan, and an Italian are in a car driving out of Nairobi. And we're driving through there, and we get to a stoplight. And the stoplight, the Kenyan's driving, I'm in the passenger seat. My Italian postdoc is behind me. He's from Naples. This is important to the story, I think. And there comes to a red light, and the driver just goes right through the light. And I say, oh, okay, it's Sunday. You went through the light. I can see that, does that mean that the police won't stop you? And he says, yeah. The Kenyan driver says, yeah, you can just go on through. And I said, oh, okay, so that means that the law doesn't apply on Sundays, that the stoplights are basically not in effect. He says, yeah, you can just go through, And I sat there for 20 seconds thinking, okay, maybe he didn't understand me. It turns out that legally, yeah, you have to stop at that stoplight, but the social norm is that, yeah, people just go through that thing. And the metaphor in terms of irrigation systems is the legal water authority might say, okay, there's a drought, you have to stop irrigating now. The social norm might be, well, if I see my neighbor irrigating, even though there's a legal rule that says no, I'm going to go ahead and also do the same thing. This is why social norms and legal institutional structures are important to understanding how these systems operate. Okay, that was a long story. Getting back to the talk then, which is the more effective use of funding to address water scarcity? So this is the fundamental question that we have here, and what I'm going to get to in terms of monitoring and governance. So one option, of course, is to build a big dam like this, but another option is to put a whole bunch of water meters in place. Another option is to fund a whole bunch of stakeholder meetings, or to put a whole bunch of water meters in place. And the point I want to make here is drawing from some of my work in Kenya, is that this is a place that beautifully has applied these design principles for common pool resource systems. Clear boundaries, conflict resolution mechanisms, recognition from formal authorities. And yet, in this place here, which is one of the most semi-arid in the world, goes from 800 millimeters of rainfall here around Mount Kenya down to 200 millimeters. Pastoral societies who are drawing water out of the river and trying to grow tomatoes on the side of the river. How does this system kind of operate, and is there adaptive governance? What we found is no. And the reason is, despite the fact that they meet all these design principles, there's actually very little infrastructure for monitoring who is taking how much water out of the river. So what we can find here is that in the absence of effective monitoring, it's nearly impossible to implement what is called pay-as-you-go arrangements. That is, we don't know how much water you're using versus I'm using, and so we can't charge you for how much water you're using. Everybody gets a flat fee. And then in the absence of pay-as-you-go, there's little incentive for anybody to implement water conservation measures. So there are these obstacles to effective monitoring in places, and my talk here is mostly leveraging these contexts from developing countries. One is the cost of locally suitable instrumentation. The second is the transportation costs involved with collecting measurements. And so there's basically this need for low-cost solutions, both in terms of financial costs and in terms of time costs. And there's some development here from a variety of groups. I put up a couple of pictures just for a couple of them. One from this TAMO group, the Trans-African Hydrological and Meteorological Observation Network. It was trying to deploy many sensors, thousands of sensors across Africa, and then some group from colleagues of mine at Princeton University developing low-cost environmental sensors. But the story here is that frugal innovations may change the way that these systems operate in terms of giving better monitoring options for improved governance. And the reason why this is possible, in part, is because of the proliferation of cell phone networks. This is a slide showing the adoption of cell phone networks. So basically, these systems are able to have, for a low cost, even 10 euros for one sensor, able to transmit data in real time in Africa, which people in the United States are doubting that there's this kind of density of cell phone networks, but it is possible. Admitting that there are problems with tampering. If you leave a device alone in the middle of nowhere, people are going to grab the wires and so on, so I don't mean to make it sound like this is a perfect solution, but this is changing the way that monitoring and governance can happen in these places. So what I can say is that we are doing, and I use the royal we, we're doing a pretty good job of creating data infrastructure for hydrological data. I can go online and I can download data from yesterday for the Colorado River in 5-minute increments. Unbelievable. In Africa, of course, it's harder to do that, but there's at least a little bit of an infrastructure. In terms of some kinds of social data, there's pretty good infrastructure. That is, the FAO has tried to harmonize population data globally. We have globally gridded population data, also commodity price data, so we can put these things together in our models that are linking social and physical systems. But what about governance? So in other words, there's not even any kind of data set showing whether the presence or absence of local level water management globally, despite the fact that we know how important governance is to how people are using water resources. So what we're falling into is this curse of the case study. That is, we have lots and lots of case studies, lots and lots of examples, lots of stories. I'm not criticizing a community because I do this myself. But the question is, what are we going to learn from yet another case study? And so the important thing here is to facilitate meta-analysis of these social hydrological systems and ideally find a diagnostic approach to understanding how these systems operate. So the problem here, I call this a horrendogram. It's when you have a conceptual model that's so horrendous that you can't figure out what's going on. Even worse is if you make an analytical model from this and you have so much complexity in your model that you can't identify what's happening in your model. So how do we take this, but this is, in some ways, this is what's happening in the real world. How do we take this and unpack the governance? And I don't mean to promote this as the only way to do this, but one way is what's called the social ecological systems framework. And what this framework is trying to do is take social systems and physical systems and understand the salient governance elements that are important to how that system operates. So I won't talk about this in arduous detail, painful detail, but I just want to focus on a couple things. One is the upper right, the governance system, and one is the lower right, the users. And so There's criticisms about this framework in terms of the detail, the articulation of the physical systems. But what I'm trying to communicate here is that this basically is a way to translate those design principles that have been identified to lead to, or tend to lead to, successful common pool resource governance, and make different coding schemes or coding variables for these. So in effect, I can take this SES framework and apply it to my case in Kenya, and turn these into different variables, indicators that describe the governance of this system in the context of the physical and social variables. So this isn't a new idea. This isn't the only framework. This is work from Claudia Paul-Vostel that's done similar kinds of things with the New Water project, which is now finished, but has similar kind of frameworks that incorporate dynamics, including social learning. What I want to emphasize here is this need to move beyond case studies. So the first point is, can we develop semi-coordinated data collection? And this has been done in other kinds of social ecological systems, particularly forest systems, to identify what kinds of management structures tend to lead to reduced deforestation. And through case study analysis using consistent data protocols and field data collection, more than 200 cases with longitudinal data have been used to find the successes and failures of these forest systems. To my knowledge, there's not a similar kind of system for social hydrological systems, but I'm happy to hear of situations where they do exist. The second thing is coding schemes to facilitate data harmonization. In the absence of everybody using the same data collection protocol, if you can at least create a schema to translate somebody else's data into my data and back and forth, that's alone a success. And then a data infrastructure to put this all stuff together to enable case-to-case comparison, and then also quantitative large N analysis to understand what kinds of governance arrangements are successful in those cases. A couple of examples here. I'm familiar with the GLOBE project. This is one primarily for land systems, but it's applicable to social hydrological systems. And this is one that I found just very quickly. I'm not very familiar with it, but I just wanted to pull up some examples of efforts to do so with hydrological systems. And these basically create an opportunity for you to upload your case study and put it into a library or a database. This here is just narratives, stories. This here is actually a coding scheme. And then also the Global Water Systems Project is trying to do similar things with respect to dams and reservoirs, and so this is a first step. So my summary points here are that I don't mean to be waving the governance flag and saying that it's all about governance. I'm really more of a quantitative scientist, and I started out my life as a physical scientist, so I crossed the boundaries here. So good governance doesn't by all means mean that you'll necessarily have effective natural resource management, but it doesn't hurt. In the absence of actionable information, though, or in the absence of good monitoring, even the best governance arrangement is going to fail. So how can we move forward? Well, there's no recipe for effective integrated water resource management or implementing adaptive governance. What we need is a library of cases of successes and failures to understand under what conditions, the diverse social and ecological conditions, we have these successes and failures, understanding the challenges of saying that one place here, one solution here may not work over here. But it's only through cross-site analysis that we might find these possible solutions in the future. Okay, I will stop there, I think. My last slide.
We have time for a couple of questions. I'm sure that will lead. Please speak.
You mentioned best governance. How do you define best governance?
So we can talk about, and I use sloppy language there, so thank you for catching me on that. What I should have used is this term called institutional fit. That is rules and governance arrangements that are suited to the local social and ecological conditions. So it doesn't mean that good governance is this kind of arrangement that is applicable to all places. And Lynn herself used this term no panaceas. There's no single top-down or bottom-up that's going to work. But what you need is adaptive governance, that is the ability of users to respond to a scarcity condition. And in the absence of a good governance framework, that is those design principles are indicators but not necessary or sufficient for good governance, that's what you need is the ability for users to be able to respond.
I was reading a paper, getting ready for a talk similar to what you did, and this paper made an argument that good governance, good means stakeholder involvement, democratic, good. Didn't work as effective if it wasn't managed as authoritarian.
Yeah. Let me. So if you couldn't hear, the comment was that a stakeholder-driven, local, bottom-up kind of governance doesn't necessarily lead to good outcomes, and I agree 100%. This kind of idea of the noble savage always making great decisions about their local resources is a total myth, in my opinion. There are some cases where, and there are examples from forestry, where you have to put a fence around a forest to stop people from doing local extraction. So by institutional fit, I don't mean to say that local bottom-up is always the best way, and I had fights with Lynn about this because her work and her scholars were very much driving this bottom-up approach, and I was very much advocating exactly the point you just made.
Yeah, please. Last question.
Fascinating, especially your sort of linking of sort of governance with the needs of sort of monitoring and sharing of data and information. I mean, how is sort of not only this community of scientists, but across the sort of social scientists, how can we set up that schema to enable that sharing of the data and information? And within hydrology itself, there's been great advances in the last few years about various markup languages, water markup language, hydrological features on how we can better share our data and information, but that's still not going right across those different domains. Do you have any suggestions of how we do that?
Yeah, here I had to criticize my side of the fence, so to speak, even though I think of myself as having one leg on each side. But on the social science side, there's certainly a tendency for scientists to say there's so much complexity in my local situation that I don't want to code it using this simplified approach because I'm going to miss some of the important dynamics. And the social scientists have to move beyond that kind of mindset. You have to realize that there's some utility in doing some kind of common coding if we're trying to get to this. And physical scientists have done that evolution much better than social scientists, but we're seeing some changes in the social science community as well. Thanks for your comment.
Thank you, Tom. Very inspiring talk. I'm now pleased to introduce the last speaker, Professor Quentin Grafton. He is Professor of Economics at the Australian National University and he is also Director of the Centre for Water Economics, Environment and Policy at the Crawford School of Public Policy at the Australian National University. And he is also the chairholder of the UNESCO Chair in Water Economics and Transboundary Water Governance, and is also the Executive Director at the Australian National Institute of Public Policy. Thank you, Quentin, and the floor is yours.
Thank you very much. If anyone needs to leave to go and have lunch, please do so now. I'm at the end of the irrigation channel. So there's the formal rules of 15 and 5, and I think that it's the informal rules as well. So look, I'll try and be as quick as I can on between you and lunch. So this is a little different. This is a specific case study, so to speak, but it really is going to, I think, give some insights about how we should manage urban water, in particular how we do supply augmentation. So let me just go through what it's about. So I'll talk about a supply and water demand problem in an urban context. Then I'm going to go through and talk about efficient water pricing, which will be familiar, I think, to most of us, and certainly the economists in the world. Then I'll go through and talk about how water pricing is actually done in the context of Sydney, Australia, the largest city in Australia, and then look through some models and some results, and I can give you some key findings that come from that. So just keep in mind it is a specific case that we're looking at, Sydney, Australia, but I do believe that there are insights that come from this that are generally important. So this just looks at the ratio of annual water withdrawals to annual renewable water resources. So we can clearly see it. Most people in the world will be aware there are clear issues in particular parts of the world, and that also includes where I live in Australia as well. So there's clearly some sets of issues. This goes well beyond just the urban environment, obviously includes the entire landscape or waterscape. So this is the issue in terms of demand and supply. This is just looking at the global water demand where it might be increasing. Interestingly enough, in the OECD, it's basically holding its own. The growth in water demand is going to be in the BRICS and some also in the rest of the world. So this issue in terms of what I'm suggesting about how you deal with supply and demand will be particularly relevant in the BRICS and the rest of the world. So how do we do, and what do we do in terms of balancing supply and demand? Well, this is all about thinking about capacity and infrastructure. So in other words, there's an infrastructure that's available in an urban setting, and then we have to make sure that capacity is sufficient to be able to meet the demand. And we have a particular set of issues in Australia, not just alone in Australia, but a set of issues in terms of water demands, which are of course related to temperatures, because you'll tend to use more water in terms of the outdoor use when there are higher temperatures and when there's less rainfall. And then related to temperature in terms of inflows, of course, is the supply. So if there's lower inflows into dams, in terms of storage areas, you'll have a lower supply. So you get a double whammy in those contexts. So when we have these periodic droughts, which we do in Australia, then we've got a particular problem. The question is how you manage that, both in a capacity sense and then also in the context of the soft side to it, which is in terms of your policies. So this gives you some sense of what's actually happened over a period of time between 1998 to 2012. And if you were at the session this morning, she would have talked about the Millennium Drought, which lasted about 10 years in southeastern Australia. But what you can see here is the level of water in the dams. So a falling of water in the dams, this is the 50% level, and then there's a reaction at some point in time, and there's those two red lines, the arrows represent the reaction. As the capacity of the dams fell in terms of how much water is in storage, then the reaction was to do supply augmentation. And so the standard engineering approach is, well, we're getting less and less water, so what do? We need to do some supply augmentation. So it's the engineering approach to this. What I'm going to emphasize in this talk is that we need to think about the socioeconomic side to it as well, and we would have ended up with a much better set of outcomes. So that arrow there was when they decided to build the supply augmentation story I'm about to give you, a desalination plant in Sydney, and that's the red arrow when it was actually complete. And if we keep on this trends here, we're running out at 98% of the water. The dams are about 98% full. Okay? So let's go on. So here's the picture of the desalination plant that's been operational, or this has been built in 2010. And this is the desal plant. It takes obviously seawater, goes through reverse osmosis, and then provides that water to Sydney households. The approximate cost, capital cost of that was approximately $2 billion Australian dollars, so it was not cheap. And the operating costs are fairly substantial as well. And so that's the capacity supply augmentation story. Now let's look at the other side to it. So that's the supply side in response to a drought. Let's look at the demand side and the response to the drought, okay, and what was being done. So economists have a way of thinking about this in terms of marginal cost pricing. This idea of marginal cost pricing has been around for a long, long time. And so the idea is to say that you should price your water at the marginal cost. Now it could be a short-run marginal cost, or it can be long-run marginal cost. That's the sort of way that economists talk about it. And of course, there has to be an overlay there as a set of issues in terms of monopoly pricing. So in other words, that if there's a single source supply, which is typically the case in urban environments, how do you regulate that price to make sure that there's no market power and be able to extract rents from households who are unable to go to other sources. And so there are various ways that these systems have been implemented imperfectly. So here's the economic approach, and then here's the imperfect ways it's done. Typically there's a fixed charge, typically, a fixed charge, and then there's a volumetric price, which is how much which is your essentially your marginal cost for any additional supply into the system. So now let's look at the Sydney case. So that's the case of water pricing in general. Here's the case in Sydney. So in Sydney, they've got what I would call average incremental cost, which they have defined to be long-run marginal cost pricing. Now this is relevant to the issue of supply augmentation because the higher the price, all else equal, the lower the demand. So price is going to affect your water demand, which will then determine, of course, when you undertake your supply augmentation. They're not disconnected, they're in fact closely connected. So how do they do that? Well, they just simply take the least cost investment to equate demand and supply, which in the case was a desalination plant, and then they divide by the volume being produced out of the desalination plant, and then that determines the price that's charged to the marginal cost that the households have to pay. That's what they call long-run marginal cost. Of course, the issue with this, as you probably see, is that this issue here is the issue in the context of uncertainty, because this has to be related, of course, to the uncertainty in terms of the weather events. So in other words, if you don't take that into account when you make your supply decision, you can actually prematurely undertake your supply augmentation. And if you don't take into account that households respond to price, then also you can have premature supply augmentation. And in both cases, that's exactly what Sydney Water did, and the CIS state government, New South Wales did. They ended up with a bad outcome. And so, what is that outcome? So, let's just quickly look at those pricing issues associated with Sydney Water. So the first case is they talk about a long-run marginal cost. Of course, it's not a unique number. It's going to be determined by its weather realizations when you actually do supply augmentation. So that's clearly a problem. And then the issue is if you don't have a sufficiently price rate being raised as the dam level falls, so your price is constant irrespective of how much you have in the dam. Okay, you're not taking into account the water scarcity. Okay, and therefore, how do you resolve the demand issue? The demand is going up. You do it through rationing. You do it through non-price mechanisms, which imposes costs on consumers. And so those welfare losses can be quite substantial. In the case of Sydney, did some numbers published a few years ago, that the welfare losses in Sydney in 2004, 2005, in aggregate, approximately $250 million for that year alone, from imposing water restrictions in terms of how water is used by Sydney households. So what we tried to do in this particular case is to model this particular problem. It's a counterfactual because the Sydney Water made a determination to actually build a desalination plant in 2007 and became operational in 2010. So this is a what-if question. What if they had done something different in terms of water pricing? What would have been the difference in terms of the social surplus with the desalination plant and the social surplus without the desalination plant? And the way you get the balance in terms of supply and demand, of course, is adjustments with the price. Okay, so this is the way that it's done in terms of stochastic dynamic programming. And this is the thing that we're specifically looking at, is this is the issue of social surplus. So this is the demand of the households, and this is the number of households, this is the individual demand, which is broken down into indoor and outdoor use, which is relevant because they're different demand elasticities. Then this is the marginal cost from the dam in terms of how much has been withdrawn. This here represents a marginal cost associated with we call it a backstop technology. So if you were to run completely out of water in the dams, if you completely run out of water, where would you go? Well, you go to basically importing water from outside of the catchment at a very, very much higher cost. And then in terms of the desalination problem, we have another value function. We'd be able to add in here the amount of water that's coming out of the desalination plant. We've got two value functions which you can then compare and then see the differences in the social surface between the two. And so here are the results. And the results are quite shocking in terms of not having appropriate pricing and undertaking supply augmentation at a premature point in time. So if you just look at these 2 points, so these are the two different realizations. So one of them is a long-term data series that starts in 1919 and goes to 2008, and the other one starts in 1969 and goes to 2011. So one's a shorter series, because it'll be a longer series. Over the longer series, it's a wetter distribution. Over the shorter series, it's a dry distribution. And have a look at some of these numbers. So they all have the same cost in terms of the desalination plant, which is approximately $2 billion. and that plant produces 250 million litres per day. There's an option to expand that to 500 million litres a day, but it hasn't happened yet. And then you have here is the change in the surplus, social surplus. What it's basically telling you with those numbers, and they're quite large numbers, is that there is in fact a loss associated with the building of that desalination plant, at least when it was built. Started to be built in 2007. And then if you add on the capital costs, because the capital costs are not included in the value functions, you add that up and then you get a present value of losses, which works out, depending how you want to do those numbers, it's over $2,000 per household in Sydney. So these are very large numbers. We're quite well off in Australia, but more than $2,000 is still quite a lot of money even in Australia. I'm emphasising the Australian aspect of this is because if you see those demands in terms of global water demands going up, okay, almost all of those countries have lower incomes, substantially lower incomes than we have in Australia. So if we're having substantial costs in Australia associated with premature supply augmentation, there'll be even bigger proportional costs associated with that in some of those countries in the BRICS and the rest of the world. And so then the issue is well, would you build a desalination plant? And so this is a question, again, associated with the weather realizations, and it depends on what your realization is. And yes, there's a possibility, if there was the driest 20-year period on record, then you'd be building the desalination plant in 2027. So still some time to go before we're building it, and in the weather realizations, it's a long time into the future. That's building in some population change as well over that period of time. So where does that take us? Well, this looks at different prices between the different contexts in terms of desalination. And with desalination and without desalination, obviously the without desalination is the counterfactual, and there's a difference there of approximately 30 cents per kilogram. So the key findings, what do they tell us? Well, first of all, is that the pricing approach that's been used in Sydney Water, and let me emphasise that's not just in Sydney, that's true pretty much across the board in Australia and in many other countries as well. So it's not a unique to Australia case. That's inappropriate for long-term water pricing in the context of uncertainty. It's particularly acute in the Australian context because the weather realisations, we have very long periods of drought in Australia, much more so, more pronounced than in many parts of the world. So it becomes more of a problem for Australia, but it is problematic in other places as well. And so the social surplus, it depends on the parameter numbers we want to, parameter values we want to come up with. It's actually considerably more than 3 billion, but let's say it's 3 billion plus. That's a big loss. And now, as I said, that's about $2,000 per household. And so what does that take us? Well, that's 30 cents a kilogram. I think the bottom line here is that if we do our pricing right, we focus on the pricing as one, not the only, but one important instrument in terms of managing demand, that will also have a positive impact in terms of when we do supply augmentation. And put the two things together, then we end up with a good outcome, or a better outcome in terms of consumer household welfare. And then I think, given that we spend about $75 billion a year on water infrastructure globally, I would suggest to me that those welfare gains could be quite considerable. Thank you.
Thank you. We have time for questions. So, first,
if Sydney Water, what would they say?
What would they say? Oh, okay, so Sydney Water don't like my work. Okay, so their response is about, they come back with a reliability argument. So they come back and say, well, with desal, we're buying ourselves an option in the sense that we've got this supply that's ready to go, and it's there waiting for it, and we're prepared to pay for it. Then my response to that is, well, how much are you prepared to pay for it? Because what we're prepared to pay is a very large sum of money, and I would argue that if you want to take a democratic turn to this, if you pose to the households in Sydney, do you want to have a desalination plant and it's going to cost you, present value terms, more than $2,000? I suspect you wouldn't have got the outcome. But the reason that the desal plant was built, the real reason the desal plant was built, is associated with, and we're talking about sociohydrology, is the socioeconomic side, the political side to it. Because in 2007, there had been water restrictions in the city, quite severe water restrictions for about a 3-year period. And so the state government, which owns city water, made the decision to build the desalination plant in response to those water restrictions and ahead of a state election. Okay. So that's the idea of showing that they're actually doing something ahead of the election. So that's the complication of how you get these sorts of outcomes. Yeah, that's right. But that was saying that the time that decision was made, that this information, well, in the way I've given it to you here, I didn't have that. But that information was provided to the people making those decisions. They knew that ahead of time, and they still went ahead with the decision.
There was Gunther, and then
my question is related to the previous question. You were saying there are better outcomes. I would argue there are more economic outcomes, because you frame it simply as an economic problem. Could you expand it to include politics or social criteria to make it a more broader problem?
Yeah, but I believe you can and you should, but there again, I think I hinted at that in terms of what people would want. It's not for me to tell city households what their preference functions or what they want, okay? Typically, in a democracy, we have the elected officials make those determinations. I'm countering that by saying I don't think they make the right decision. But ultimately, to me, you'd have a survey. You could survey city households, either before the decision or, in this case, after the decision, and see where they would land on that. It would be for me to tell them if people want to value reliability really highly, and they can pay their, more than $2,000 per household. I don't live in cities, so I don't have to pay for it. But that's the way I think you do. I mean, I think you want to engage households, you want to engage people in this, and part of the problem is that you didn't get that engagement process. The engagement was basically from the issue of water restrictions. And the reason that they focused on water restrictions is they thought that this was temporary, which it was. It did rain, okay? But it went on longer than they initially thought, and then they started to press the panic button because the state election was coming. And it wasn't unique to New South Wales, which is where Sydney's located. It was also true in Queensland. It was also true in the state of Victoria. It was also true in South Australia. And in quite different cases in Western Australia, where there is a clear secular trend downwards in terms of inflows, which is not the case in Sydney. There's no secular trend downwards, okay? The data does not indicate that. So yes, I agree with you. I think you want to have that multiple set of dimensions in it. Unless you do, and unless the leaders engage in terms of those multiple dimensions, you'll typically get, I think, poor outcomes, less good outcomes.
We have 2 more questions. Peter, please.
Thank you. A lot of the new water supply augmentation projects are lumped, they're big.
Yes.
But in this case, with diesel, you can also, it's scalable, you can also, the economies of scale are limited. So have you also considered that you take some smaller ones and you put it online in a temporal perspective? Maybe your benefits or your cost may be much lower.
I mean, to some extent it is scalable, and there is 2 modules, the 250 milliliters per day and the 500. But what's not so much scalable is the infrastructure in terms of piping in the water and then making the connections into the system itself. And so when they built the desal, they built it at a higher capacity, which they actually haven't needed.
We have a question there.
Rather than to this question before, I think you do have a better argument, or not better, an additional argument. I'm very impressed by your calculations of the cost, because in the real world, at the end of the day, it's really powerful, and you need to calculate that and show that it's more expensive than what they're doing. I'm also critical of desalination. You have the argument also that desalination really keeps you away from starting to implement demand management. That you continue your supply management. And the same case in Israel, refusing to implement demand management. Why do they need to use 280 liters per day? United Emirates, we heard today, 964 liters consumption per day. Where desalination plants are built, also domestic consumption per capita is extremely high. So this is an important argument as well.
Yeah, thank you. And I'd also add to that, keep in mind that they didn't want to raise the prices because they had a fixed price. But of course, once they built the desal plant, they have to raise the price to cover the capital costs and the operating costs. So then the price goes up, and then the demand does get adjusted to some extent. So you end up, with, and by default, you get some demand management on the price side.